My name is Elizabeth Wesley, and I am your instructor for Climate and Climate Change. This is just a quick video to give you some guidance on the Lesson 2 technical assignment about the global energy balance. So let me share my screen and we'll get started. All right, so the figure in the assignment is a simplification of the global energy balance. So in question 2, you are asked to calculate the temperature of the surface of the Earth. In this diagram, it's represented by T naught. So this T0 is pronounced T naught, and that is the temperature of the surface of the Earth. So when there's no atmosphere, very simply the energy in, which is the incoming solar radiation, equals the energy out. And so that is a special case of this one layer atmosphere that you're to construct in question 3, where F equals 0. And so of course, F is the fraction of the emitted radiation from the surface of the Earth that is absorbed by the atmosphere. So again, F is the percent of radiation from the Earth, the outgoing long wave radiation that is absorbed by the atmosphere. And so the main question in 3 is to understand, or the main point is to understand how T naught, the temperature of the Earth's surface, changes as F changes. So as the proportion of the outgoing radiation absorbed by the atmosphere moves from 0 all the way to 1, where nothing passes through, how does the temperature of the surface of the Earth change? So Earth's temperature, atmospheric temperature. Here we have the total in from the sun, total incoming solar radiation, which matches the amount radiated by the Earth. So this is the total long wave radiated by the Earth. This total is divided into 2 pieces because some fraction is absorbed by the atmosphere. So that's given here, right? So it's governed by this F, and some portion passes through. And so that is 1 minus F, the complement of F. So 50% is absorbed, 50% passes through, 30% is absorbed, then 70% would pass through. And so we need to solve for T naught. And so to do that, we need to construct 2 energy balance equations, one for the top of the atmosphere, which is the total radiation lost to space, and one for the atmosphere itself. So for our first equation, we need the total into the system and the total out of the system. So total in, incoming solar radiation, is equal to the total lost to space, which you can see is the total radiated upwards by the atmosphere plus the total that passes through the atmosphere. So both of these together, the total lost to space, has to be equal to the total coming into space. So total emitted upwards by the atmosphere plus total passing through the atmosphere. All right, so this is energy balance for the top of the atmosphere. Total into the system equals total out of the system. So incoming solar radiation, radiated upwards by the atmosphere, passing through the atmosphere. And so we need to solve for T naught, the temperature of Earth's surface, but we can't with this equation because we have 2 unknown temperatures, T naught, but we also have the temperature of the atmosphere. So we need to construct another equation for the temperature of the atmosphere. So another energy balance equation for the atmosphere itself. And so again, energy in has to equal energy out. So what is the total energy coming into the atmosphere? Well, it's the amount being emitted by the Earth times F, right? Because F is the fraction of the energy coming from the Earth that is absorbed by the atmosphere. So total emitted by the Earth, which is just this Stefan Boltzmann, right, for the Earth's surface temperature. But times F, because F is the proportion of this absorbed by the atmosphere. So this is the total into the atmosphere. And then the total coming out of the atmosphere is this here, right? Because in this model, we are considering this a perfect black body, which is a theoretical perfect emitter of radiation. The atmosphere is emitting energy equally in all directions, which in this case is up and down. So we have equal amounts radiated up and down. And so that, again, is governed by F. And so we have two of these, right? So here we go. So the total absorbed by the atmosphere equals the total radiated by the atmosphere. And so just simple algebra, you can combine these terms. And simplify here, right? So you have two of these, so you can just multiply by 2 and take away this, right? So this and this are equivalent. So let's get rid of that. So now that we have two equations, we can solve for T naught. And so what you need to do here, we need to get rid of this atmospheric temperature in this equation, right? Because we're only interested in T naught. So what we need to do is rearrange this equation so that we can substitute for this using some version, some form of T naught, right? And so you can see this is exactly the same except for the 2. So all we have to do is divide by 2 on both sides. And so if we do that, can divide by 2 here. Oops, what did I do? There we go. So we divide by 2 here. And then if we divide by 2 here, just gets rid of that 2, right? Because 2 divided by 2 is just 1. So now you can see that this is exactly equal to this. And so since this is equivalent to this, we can substitute in here with this. All right, so here is our full equation. And now we can remove this because we can substitute in this term, right? These two things are equivalent, so we can get rid of this and put in this. And now we only have T naught. And so now what you're going to need to do is, again, just using basic principles of algebra, you need to rearrange all of this so that on one side of your function, you just have T naught. And then on the other side, you're going to have whatever this ends up being when you isolate this term, right? So you're going to have to move everything over to this side through multiplication and division, and then eventually take the quarter root. So you're going to have t naught equals some function of f, right? So then what you're going to be able to do in Excel is calculate t naught based on different values of f. So we know that f, because it's a percentage or a proportion, ranges from 0 to 1. So you will be able to calculate t naught for different values of f. So what I did is I calculated t naught for f in increments of 0.1. So at 0, 0.1, 0.2, 0.3, all the way to 1, you calculate t naught, and then you're able to chart those values. So on the x-axis, where you have your independent variable, you will have your values of f from 0 to 1, and then on the y-axis, you will have your dependent variable, which is Earth's temperature at the surface, this T naught, right? So you're going to graph or plot T naught as a function of F. And so that way you can see as F changes, how does the temperature of the surface of the Earth change? If you need help doing that in Excel, I included some resources in the lab assignment. There's also abundant help online, so I encourage you to look there. Please continue to post to the discussion board if you have more questions. Hopefully this clarified things for you.